This is Group 17's engineering study of battery factory excellence.
This is the timeline showing the events leading to the accident. On 24th of February 2017, the crane engineer, Mr. Tavorta, began installing the crane. He realized that the installation kit did not contain instructions on the tightening torque of the stud bolts. After failing to contact the crane manufacturer, Redwing Lifts, his supervisor, Mr. Stripple, suggested him to tighten the bolts to 560 Newton-meters. He realized that one bolt was missing. Thus, a bolt from a similar crane model was provided by the branch manager, Mr. Anderson. During the installation process, the bolts and nuts used were of size M24 instead of M30, as shown on the manual. On 14th of March, the HGV engineer, Mr. Akinfina, inspected and commissioned the crane. He could not test the crane through its full 360 degrees range of motions due to pallets blocking the way. On 5th of April, around midday, during lifting operations carried out by the crane operator, Mr. Tatton, the crane fell and injured the operations manager, Mr. Vance.
In studying the cause of the crane collapse, several factors were analyzed. Force and moment calculations showed that the crane was not overloaded at the time of the incident, thus should not have failed at the weight lifted. Checks on the tightening torque used on the bolts showed that the bolts were sufficiently preloaded to a value of 135 kilonewtons, which is greater than the incident load of 120 kilonewtons. Looking at the bolts and nuts used, it is found that the grade of the nut used for the bolt was not in compliance with national standards, as a lower grade of nut was used with a higher grade bolt. Furthermore, the size of the fasteners used were not the size indicated in the installation manual. It is concluded that these factors caused a chain reaction which led to the collapse.
Regarding the maintenance and operation of the crane design, the crane inspector carried out an overload test with a load of 2,000 kilograms, which exceeded the intended load by 125 kilograms, possibly contributing to the failure of the nuts. Also, the bolts did not get retorqued following the overload test, causing possible loosening of the nuts, followed by reduction in their preload values.
Furthermore, for the legal aspect, we assess XFIS 47's compliance with the lifting operations and lifting equipment regulations. We concluded that the main regulations not complied were Regulation 4, being not to exceed the limits of strength or stability of the lifting equipment. This was not complied as the crane's new base was installed on the old plinth without checking the integrity of the original structure. Additionally, Regulation 8 clarifies that each lifting operation needs to be planned, supervised, and carried out safely. This was not complied as the crane was operated while the driver and Mr. Vance were under the load and the maximum load limit was not reduced to a safer limit as asked by high-tech cars. Finally, Regulation 9 requires all lifting equipment to be subject to thorough examination at various points before being used. This was not complied as XFIS 47 was used before commissioning and Mr. Stripple, being the competent person, did not properly check on torque or bolt stability.
A new PDS was created where we will talk about 5 main aspects of this new design. It must offer a better stability on the base, as well as safer working conditions. It should be installed when Hydrix wants to continue those operations. Safety is an important factor. Indeed, we considered the risk on the workers' health, and to answer to this criteria, we created and extended a safety zone with a fixed radius. Then, the new design will depend on its installation. It must be easy to assemble with fixed instructions and measurements. The maintenance must be considered, and it must be verified through checkups with a pre-established checklist. Furthermore, commissioning is crucial as lack of it can cause failure of a crane. Different objectives can be set, such as realizing to full extent different tests, such as the 360 range motion. Finally, the performance must be considered by considering such as setting a precise load capacity without overloading the crane.
When we were looking at our old design, we found that the main issue was the dependence on the bolt joints for stability. We therefore decided to add hydraulic stabilizers so that the weight of the crane and the load will be distributed between the four stabilizers as well as the bolts. The hydraulic supports are composed of a piston mechanism, which also has a pressure gauge linked to an alarm system. As we want the solution to be safer, we wanted to check if the four stabilizers would be able to hold the full weight of the crane and the loads if the bolts were to fail again. So here's our free body diagram that we use for our calculations. We can see that we simplified the crane, and we now have three different weights. Weight 1, which corresponds to the mounting block, which is made of steel. Weight 2, which corresponds to the weight of the crane. And weight 3, which corresponds to the weight of the pallets. We can also see theta 0, which corresponds to our boom degree angle, which is in the middle of the diagram. And we can also see that we considered four normal forces, drawing them such as A is composed of A1, A2, B is composed of B1, B2. Our measures are these specific distances because we considered our new safety measures. So this scenario is therefore in the case where the boom of the crane is at its maximum length of 8 meters. We then proceeded to find the reaction forces and moments in A equations. From those equations, we then obtained the equations for the forces applied at each stabilizer in function of the boom degree, which is what we plotted in the graphs.
The new design uses a hydraulic system to fix the displacement of the crane. It relies on the use of fluid pressure to transfer force to extend and retract the legs as necessary. The system is further capable of withstanding shock loads without moving the leg, thus can act as a stabilizing system in the case of failure.
So as we can see, for the calculations for maximum pressure and piston selection, we have to resolve both the normal at A and the normal at B into resultant forces into all of the legs. As such, we were able to calculate the maximum force that would be experienced by the leg to be 123.54 kilonewtons. Thus, the maximum force that the leg was withstand is 123.54 kilonewtons. Therefore, we selected a hydraulic piston accordingly. We used a piston bore diameter of 0.1524 meters, and as such, we calculated the maximum pressure in the piston to be 67 bar. Existing hydraulic cylinders can handle a pressure of 210 to 690 bar, and specifically the Park HMI, which we selected, operates at a max operating pressure at 210 bar, which is more than enough for what we actually need.
Finally, we thought that the safety provided by the new crane design was limited, and thus we considered new external safety measures. This consisted of adding a 6-meter safe radius from the center of the crane, surrounded by a 1-meter high gated perimeter. This would ensure clear indication of the restricted loading zone and thus prevent any worker from getting inside. It would also be large enough to reduce the risk of an accident in case of the crane's full mechanical failure. Finally, we've designed a conveyor belt system to load and unload the battery pallets safer. How it works is when the truck unloads the batteries, a worker unhooks them from the crane, placing them on the old battery area shown on the left of the diagram. These batteries will be transported to the middle area of the conveyor belt as shown on the diagram, where the conveyor belt would be stopped. The forklifts would be then used to collect the old batteries for recharging, and similarly used to place the new batteries on the conveyor belt to load them on the truck. The loading of the full charge batteries would occur at the same manner, but in a reverse order direction as the old batteries. The new battery area would include a weight measuring system to check the weight of the battery batches before loading. These are the list of references we used. Thank you for listening.